have the joke for today. And spider bees have sticky hair because they use honeycomb.
Brush their hair. Huh? Yeah, that sounded familiar. New joke. I don't know. That one sounded familiar.
Is this a really good one?
It's just so good. I've got a whole nother bag of them. If we need 12.
Okay, how much does a rainbow weigh? Not much. It's pretty light.
There you go. Science related. It's good. All right, y'all. Welcome back. Glad to see you all. Hopefully that means that things are smooth outside of class for you. If not, I am sorry. And please let me know if it has any effect on you in this course. It seems like the hurricane was fairly tame, but fairly tame, it's an average distribution, right? For a lot of people, it went decent. For some people, it really did. And if it really didn't, again, let me know. I want to, this is stuff. Anytime there's stuff outside of your control, I do not want it to negatively affect your performance in this course. So I want to work with you and all those kind of things. So keep that in mind. Lots of announcements. The test. So I sent an announcement. The test grades are all posted. So if you all go and look and all those things. The free response grades are posted, and that's out of 40 points. The multiple choice is posted. That's out of 60 points to match the percentages. And then there's one that just has it out of 100 points just to make it easy to see, all right, what I actually get on the entire test. So I tried to split it up so you can see how you did on individual portions. In general, there's a pretty strong correlation between the free response and multiple choice. People's grades tend to kind of, it was maybe grades increased or decreased by plus or minus 10 points after the free response, and that was kind of the maximum amount. Most people's grades didn't shift by that much, maybe like 4 points or 3 or something like that. Free response grades were very nice, like they were overall very good. The average, I think, on all of them was around an 80%. So that was good. The second one, and I can't say too much because I still have one more makeup I have to do. The second one had the lower average of all the three, if you remember which one that is. If not, I can tell you individually or I'll mention it more. So yeah, there was no curve or anything on the free response because largely it was pretty good. I graded a third of them, so I kind of got to see how people did on them. And it was very much either you kind of knew what you were doing and you got most of the points, or you didn't quite know what you were doing and you didn't get many points. It was kind of very dichotomous in that way, which was interesting. But anyway, all that to say, overall very happy with them. Great job, everyone. If it didn't go well for you, I am here for you, as always. And so is Leo, and so is Angelina, and so is Sark Tutoring, and all those things. The most helpful resource is people when it comes to learning. Individual tutoring is always the most beneficial, and you have 3 places you can go to it. You can go to my office hours. You can go to the help room. So not just Leo, but there's a whole help room with people in it, and I posted that forever ago. If you go to the announcements, there's a whole schedule when you can kind of show up there. And then there's Sark Tutoring. Those are the best places to go. Individual help is going to be the best pretty much always because a human being has the most flexibility. You are a complex individual, and the challenges you're encountering are going to be unique to you. And so a human can help identify what those challenges are and kind of help you along the way. So that's this. Oh, and then assignment-wise, I sent out an announcement. Everything has gotten shifted back a week is basically how that goes. So if we go to the simple syllabus, I have updated this with at least when all the content's going to be covered. I've also updated all the assignment dates. Apologies on this quiz. I thought I had updated it for this class to at least be for the... I hadn't. The last quiz date, unfortunately, I thought I'd updated the one that we haven't even finished covered everything. So it was like due in quotation marks this last Saturday. I have shifted that due date. I sent that in the announcement. So quiz 6, work and kinetic energy. I unfortunately hadn't realized that it was still due this 12th. I have shifted that all the way until the 23rd to match our usual structure where we will finish the content today. And then you all have a week to kind of prepare and do the things. And if you're like, but I already did all my attempts and all that stuff. I manually went through and everyone that had attempted it, I gave them as many attempts. I made it so they still had 2 attempts. Okay? Everyone that was proactive and was like, okay, I saw the due date, I'm going to go ahead and still try to do it. I went ahead and added attempts to them so that everyone still has, on the 23rd when it opens, everyone will still have the 2 attempts. So if you're proactive and you kind of still did it, great, you got some extra opportunity to see the questions. If not, you're not penalized. So there you go, all works out. So moving forward, quizzes will open on Wednesdays and they'll close on Wednesdays because just the way that things got shifted from all the things is that we will start stuff. So this Thursday we'll start potential energy and conservation of energy. And then this coming Tuesday we'll finish it. So then the quiz will open and you'll have a week. So it still follows the same time structure. We're just off a bit and that's fine. All right, so boom, 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 scroll on down. I want to point out the major thing on here, which is test 2's exam date or exam 2's date, whatever. Whether you call them tests or exams, I don't know. I don't know the difference between them. They're all the same to me. All right, zooming in is ineffective. All right, everything is shifted. Y'all can look at it on your own devices if you want, but everything is shifted back by a week. So, here's 16th is tomorrow. So we're going to finish working kinetic energy today. And then another week, then another week, then another week. And exam 2 will be November 12th. Tuesday, November 12th. So that is in 1, 2, 3, 4 weeks. There it is, November 12th. Because obviously I've had to shift these things. If there's a conflict that has arisen that you know about, you had planned travel at that time because I told you the test date was different before, whatever. Let me know if you know there's a conflict now. Just so I can work with you on that. And I'm not going to penalize you if you've kind of know at this point that you're not going to be available then because you planned for the old test date. All right. Also, I had to cut a tiny bit of content, so I am not going to try to cover the same amount of content in that time because we lost some time. So I just cut off some rotational stuff at the end. I got to figure out exactly what that's going to look like. But when we get there, what I cover is what I'll test you on. I'm not trying to cram the same amount of content in less time. That's unreasonable. I'd rather you all learn less things well than a lot of things not really well. That's kind of the mindset I have with this. At the end of the day, it's the skill set I'm teaching you that's important, not the specific concepts. You will use some of these specific concepts, but like half the things I'm going to go ahead and throw out 80% of the stuff I'm teaching you all, you might not ever use in a class in the future. Like, unless you're mechanical engineering, civil engineering, you're going to use these things all the time. But like computer engineering, you're probably not going to need this stuff. Comp sci, not 80% of the content I'm teaching. But the way of thinking through this, the problem solving, that is relevant to every single one of you all. And even with my own major, being a physics major, that's the most important thing I learned. How to think. That's really what I'm teaching you all how to do, is how to think. Everything is just a context for doing so. All right, fantastic. So there you go. There's logistics. Any questions about everything getting shifted? Yeah.
I think before you said that the labs are going to be on Tuesdays. Is that
the labs are still Tuesdays. No, thankfully, the labs are still going to be on Tuesdays. So, for example, we're going to do a lab today. Because we lost a whole week, everything got shifted by a week. So the first hurricane shifted everything by a day, and then the next hurricane by a week. So we're still in that like 1 day off kind of thing. That's a good question. Final exam, as far as I am aware, UCF has not changed anything about final exams. So as far as I'm aware, this is still our final exam date. They have not sent out anything about dates getting shifted. So I'm operating with the same knowledge as you there, the assumption that that should be the same. Okay, 2 nifty things, science today stuff. So the Nobel Prizes came out. If you weren't aware of that, every single year they award Nobel Prizes. There's a Nobel Prize in physics. Interesting enough, there's been if you haven't seen what it is, it's something that's very popular right now. It's AI. So yeah, the Nobel Prize in physics, which is kind of interesting. It's in developments in AI, large language models, which is kind of weird because, is it physics? I guess they used physics principles it was physicists and they did use physics principles to contribute to that field. But it's kind of interesting. The chemistry one was also in using AI to do chemistry related things. So one of the most interesting things about the Nobel Prize is it shows the values of some subset. I don't exactly know who's choosing these things for sure, but it shows us somewhat of the values of society right now, based on the Nobel Prizes. So that's kind of interesting. And then the other interesting thing, I guess there's lots of interesting things. SpaceX did their big launch and they caught their rocket. That was cool. And then there's a rocket that just launched carrying the satellite called Clipper. So there's a couple. There's a couple really good YouTube channels called Veritasium and another one called Real Engineering, and they just did a couple videos about this. Really, really cool. So the Clipper mission is going to, I think, Europa. Yeah, one of Jupiter's moons, and it's like interesting enough. It's really radioactive around Jupiter, and they go into that in the videos. It's not because there's like uranium and stuff like that. It's check it out. But the result of that is electronics don't do well in radioactive environments. Really, really cool science. Like, check it out. They're really, really cool. The rocket launched yesterday. I don't think it's supposed to get there till like 2030. It's going to take a hot minute. Space is fairly large. You can get to places really fast in space, but you have to be burning a lot of fuel to do so. And that's weight and that's expensive. And to show the expanse, they get places pretty quickly. And you actually can, because you don't slow down in space. So you can get places pretty quick if you have enough fuel. That's the problem. So anyway, 6 years from now, we'll have some pretty pictures of Europa and they'll find out some things. They hypothesize that there's like under the surface, there's an ocean that's 100 kilometers deep on the entire surface of Europe. Like, check it out. It's good stuff. Interesting science things. Science is happening, right? All right, so there you go. That's just completely random. If that didn't track, no worries. All right, let me remind you all what the heck I taught you a week and a half ago. Because it's been a hot minute. All right, so we talked about energy. I think I finally found the quote. So Feynman says energy is that abstract idea that says it doesn't change when something happens. It's not a description of a mechanism. It's nothing concrete. It's just a strange fact that when we calculate some number and when we watch nature go through her tricks and we calculate that number again, it's the same thing. That's energy. Like, energy is a really weird idea. The more you think about it, the less it makes sense, which is kind of counterintuitive. But anyway, it's a tool. It's a tool that things stay the same. And so then energy, and we talked about work. And we said work is the integral of force dot the displacement. And I talked about a dot product, and it was the whole point of the parts that are parallel to each other. So you get this magnitude of F, magnitude of displacement times cosine of theta. And really the major thing that we needed to keep in mind here was that you care about the angle between the two. If they're going the same direction, that angle is 0. If they're 90 degrees to each other, no work is done. If they're opposite to each other, negative work is done. And so we talked through that, and we did a bunch of things with that. I encourage you all, if you haven't looked at this in a while, you're going to want to. So we did some problems on it. It was a good time. We did some integrals. And then what I left you all off with, we kind of talked this a bit. There's two different types of forces, conservative forces and non-conservative. Conservative forces, you only care about displacement. So like, you don't care about the path you take. So if I like have a rock and it does some crazy path and it ends up on the ground, or I have a rock and I just drop it, the work done by gravity is the same. Conservative force. Non-conservative force, you care about the path. If you're pushing a box in the ground, friction, you care about friction. It matters the path you take, and you have to take that into account. So, yeah.
I was going to ask, what were the things that we hadn't gone over yet for the quiz? Because
Yep. So that'll be.
Help on it.
Yeah.
So there were some things
That's going to be the last part here. So this is kind of where we got to. This is where we ended up. So we talked about work. We spent basically most of the time on work. Integral of force at distance. I talked about, I don't know if I actually got to power. Oh, I told you how to calculate the energy of your house. Whatever. I'm not like, that's a fun fact kind of situation. Power. So I did teach you all about power. Power is how much energy you use per second. It's watts, named after a guy whose last name was Watts. You have most commonly seen this on light bulbs. 11 watt light bulb, 100 watt light bulb. That is literally, you could rewrite, so, let's just take Nowadays we have LEDs. LEDs are just like better in every single way than incandescent light bulbs. So back in the day, incandescent light bulbs were like 100 watts, which is literally the same thing as 100 joules per second. Every second that light bulb is taking 100 joules of electrical energy and converting it into light and heat. It's not burning energy. It's not destroying energy. It's changing it from one type to the other. Anytime you talk about power, it's literally I'm taking some type of energy and changing it to another type. And how much am I converting per second? So nowadays, though, LEDs are like 11 watts. And again, that's just 11 joules per second. They're 10 times more efficient, which is awesome. Like, that saves you a lot of money. It literally costs 10 times less for you. But yeah, when you get charged your power bill, they take that wattage and they multiply. They get it in kilowatts, they multiply it by the hours used, and they multiply that by the cost of kilowatt hours. So for example, this will take me 5 seconds. Say you have a 100-watt light bulb. That is 0.1 kilowatts. Same thing. All I did was convert it. Let's say you use that light bulb for 3 hours every day. And the power bill, I believe it's between 4 and 7 cents per kilowatt hour. You all can check out your own power bill. Maybe pull it up. I think let's go with 7 cents. Is it more than that?
Yeah.
It's more than 7 cents?
Yeah.
All right.
Latest average from Duke Energy about 17 cents per kilowatt hour.
Really?
Yeah.
All right. I'm going to look up my power bill at some point. I was going to pull that up, but I'm like, I don't think there's anything sensitive on my power bill document. But before I put that on a stream, I'll check. All right, so 17 cents. And then literally you just multiply these together. So to get the cost for a 100-watt light bulb that's getting used 3 hours a day, so it's 0.1 times 3 hours times 17 cents. And I don't know what that comes out to, 0.3 times 0.17. Someone calculate it for me. My calculator is farther than maybe yours is. Yeah, it's basically... Is it 5 cents? 5.5 cents? 5.1 cents. So we'll do 0.05. There you go. That's the cost every day to run a light bulb for 3 hours. If it was a 100-watt light bulb, if it was a LED light bulb, it would be a tenth of that. So, anywho, there you go. This is how your all's power bill is calculated. It's based on how much electrical energy you are using in all your devices. Anywho, also if you buy very relevant for the hurricane, a generator tells you how much wattage it can output, how much energy it can convert from the fuel to electrical energy every second. My generator I had was 3,750 watts. And it has a peak wattage of 4,150 because when you first turn on appliances, they take a little bit more juice to get running. Anyway, fun things. So to that end, wattage, very, very relevant to every single one of you. I don't care what you do. You're going to be buying light bulbs. And you're going to be paying electrical bills, assuming you pay electric. I don't know why you wouldn't. If you become independent, you will pay electric bills. And that didn't work the way I wanted to. Anyway, yeah, what's the question? So it's yeah. Ooh, so it's 51 cents?
No, they're supposed to be.
Ooh, is it this cheap every day? No? All right, people are disagreeing with you. I think you got outvoted.
Isn't there a 4
Yeah, that divides by 10.
Yeah. No, it's good though. I very much appreciate you mentioning that because look, people make mistakes. I'll double check it at some point. Anyway, but there you go, y'all. That's how you calculate this. I'm not going to bother with this question. Let's take attendance. And while we take attendance, I'm going to look up my electrical bill. I'm not even joking. I'm like, man, that's... Because I could have sworn I looked it up before and it was 7, when I taught high school last year. Okay. Yeah, so let's see. I have Duke. Yeah. Does anyone have? I thought everyone had Duke around here.
OUC is in Orlando.
Oh, interesting. Okay. Yeah, electrical is interesting. You have no negotiating power there. It's not like you can choose a different electrical company. You could get a solar panel. That's right. You can make your own energy.
Oh, because it's because
Okay, so my electrical was 14 cents. If you exceed 1,000 kilowatt hours, you have to spend a little bit more. So the first 1,000 kilowatt hours with Duke Energy, you got to pay an energy charge and then a fuel charge. The energy charge is like paying for the company. The fuel charge is they literally are burning fuel to make it, and they like put that cost on you because that's just how they put it down. But that's like a 1-to-1. That's now like upscaling. If you go above 1,000 kilowatt hours, everything after that is a little bit more expensive by like 2 cents or something. So if you use less energy, it saves you money in 2 ways. All right, Leo's got you. If your thing didn't work, same old. Let's learn about work and kinetic energy. Wrong thing. All right, great news. This next section is going to be pretty straightforward, honestly. I always hesitate the word. So first, we got to introduce a word that you all have hopefully learned before. How does an object gain kinetic energy? Think back to your middle school, high school years. Maybe elementary. I can almost guarantee every single one of you have seen this word. If not, that's fine. I'm going to teach it to you. It's all energy, right? It's all energy. So is it go faster, go higher, charge it up, or absorb heat? Then go with the obvious answer. One of these you can maybe make arguments for, but it's a little silly. How does the entire object gain kinetic energy, not individual pieces of it? All right, we'll go 10 more seconds. Fairly straightforward problem. 5, 4, 3, 2, 1. All right, so the answer is going faster. The word kinetic means movement. Kinetic is motion. If you ever see the word kinetic, it's motion. So if you go faster, you gain more kinetic energy. That's just seeing there it is. You can make an argument that temperature is a measure of the average kinetic energy of the particles in a system, but that's what it's like a technically, and then you kind of like push up, whatever. We're not going to get into that. All right. It has to do with motion. Fantastic. It's a measure of the energy of a moving object. Okay. Here's the derivation for kinetic energy. I'll just kind of walk this through. You don't need to know it, but let's just look at one piece at a time. This is our definition of work. That's nothing new. I then substitute F with M times A. We know that because we just did a test on that. I then substitute A with dv dt because that's the definition of acceleration. These are all definitions that we've learned at this point. I then do some little clever kind of things I include a dx, which seems a little silly, but it's useful. We'll see why. Dx over dx is just 1. I'm allowed to do that. I'm allowed to multiply by 1. There is a reason I have this derivation typed out here. I do not have this derivation memorized because, again, you got to decide to multiply by dx over dx. That's kind of a weird thing to do, but it all works out. Boom, on to the next slide. We rearrange the terms. So we've replaced f with ma, we replaced a with dv dt, we chucked a dx in there for reasons. We rearrange things. So we take this dv and this dx and they swap places because it's multiplication. We're allowed to do that. Ain't nothing. We're allowed to totally swap these things because multiplication says the order doesn't matter. So great, we swapped those two things. Hey, dx dt is v. Dx dt, that is the definition of velocity. Oh, and some things cancel, I think. Do we cancel things at this point? Yeah. So this dx cancels, they're gone. Wow, where'd they go? We got rid of them. All right, great. Now we got this dx dt left over. Hey, that's the definition of v. All right, so all these steps, all these individual steps aren't complicated, but it's, we're just doing a bunch of them in a row. That's all derivation generally is a bunch of steps in a row. And now I get to ask you a question. What's the integral of mv dv? From VA to VB. Integrate that. We just derived that. And just to remind you all, this is what we're doing. Work, we started with work. From this derivation, we found the following. That work equals this, and now we're finding what that right side equals. Actually doing the integral. What is that integral? It's a very, don't overthink it. It's a very straightforward integral. In this case, mass is not a function of velocity. The mass is not changing with velocity. Did you clarify that? Yeah, it could happen. Yeah. They would be indirectly related for sure. All right, cool, y'all. We'll give you 5 more seconds. 5, 4, 3, 2, 1. Looks like everyone's pretty solid on their integrals. If you integrate this, I'm going to start using red because I think that's easier to see. Work equals the integral of VA, VB. I mean, you all got this, but just so I put it here so future generations appreciate it. V squared over 2 from VA to VB. Boom. Fantastic. Look, you all just derived the work kinetic energy theorem. Well, actually, you just derived kinetic energy. So, what is the equation for kinetic energy? 1/2 mv squared. Why is it 1/2 mv squared? It came from this. That's where, if you all have ever seen this equation, it came from the definition of work, which is kind of cool. By doing some little math tricks, some replacements and things here and there, you have just derived where 1/2 mv squared came from. It's not just like out of nowhere. It actually came from the definition of work. Work equals force dot distance. So I don't know. I always think stuff like that's cool. It's an equation again, most of you will have probably seen this equation before. And now you see that it didn't just come out of nowhere. That's the cool thing with physics. The vast majority of equations don't just come out of nowhere. They're either from an observation of reality, like F equals NA, or after that, they're all derived from those observations of realities. Now, I'll warn you, when you get to your future engineering classes, they're just going to give you equations and say this just came out of nowhere. Because the reality is the equations you're going to be working with are for systems that are more complex, and they don't have the time to teach you everything in between. In physics, if you're a physics major, every equation you see can all be you should be able to trace it all the way back to observations of reality. Physics majors, we never skip kind of any steps. Engineering, you all have to. You don't have the time to take 10 years of classes to learn where all your equations came from. That's unrealistic. But it's cool. It's just a difference, y'all. Neither one is better than the other. All right, great. 1/2 mv squared, very straightforward equation. Mass is m, v is velocity. Okay. Question to y'all. What has more kinetic energy? A 1,000 kilogram car going 30 meters per second or a 2,000 kilogram truck going 15 meters per second? I'm only going to give you a minute for this on purpose. I actually don't want you all overthink. Yeah. Which one has more kinetic energy? The 1,000 kilogram car, the 2,000 kilogram truck, or they are the same? And something I'll point out here, the 1,000 kilogram car has half the mass, but is going twice as fast. That's kind of the major point of this problem. The car has half the mass, but it's going twice as fast. What's the result of that? If you recognize that, you don't have to do any math, as long as you understand the equation. You have to show me it written out. Because you can. I'll be curious to see it. And the major thing is that the steps you're doing aren't just like to make it equal, because you can make anything equal anything. I'll be curious the logic of it too, because it very well could be the case. I haven't done that before. All right, I lied. I gave you extra time. All right, 5, 4, 3, 2, 1. Okay. So in this problem, you can literally just calculate it. You can literally just calculate the kinetic energy of each one. You know, kinetic energy is 1/2 mv squared. Great. Or you can recognize what I mentioned to you all. The mass of the car. So the mass of the car is half the mass of the truck, but the velocity of the car is twice the velocity of the truck. And then you just look at the equation and say, what matters more, mass or velocity? It's the velocity. Whatever happens to velocity gets squared. So they don't just cancel out. The car has more kinetic energy. And again, you can brute force that. You can literally just plug in the numbers and prove that to yourself. But what I want you all to recognize here is that velocity matters more than mass when it comes to kinetic energy. Things that go really fast, that gets squared. Whenever you square something, that makes a number blow up. Like, makes a number get really big really quickly. So moving objects, the faster they're moving, that's really the major thing when you're thinking about kinetic energy. Yes, the mass matters, but the velocity matters more. It gets squared. It matters, I don't want to say twice as much. It matters the square of the velocity, whatever that is, more. All right, to that end, what happens to the kinetic energy if I half an object's velocity? Does the kinetic energy become twice as big? So K1 is my new kinetic energy. K0 is my old kinetic energy. And do not fall into the trap. So for example, A says that my new kinetic energy is twice the old kinetic energy. Don't fall into the trap of mixing up how to read these things. Make up numbers if you need to. Make K0 1. It's really easy to get these things mixed up in this notation. So that's why I give you lots of problems to practice this skill. Is it 2 times the original, 4 times the original, half the original, or 1/4 the original? Yeah. And I'll show you how to write that out. You just write the original equation. For the b is, you're replacing 1/2 b. Yep, that's it. Alright, let's say you all here. Alright, hook up. Oh, that works, yeah. You can plug in random, make every variable 1. And then have those. You can do some stuff like that. Yeah, what variable here is changing? Chuck a half in front of it. That needs to get squared. Cool. Alright. Nice. Yeah, so keep the 1/2 though. So don't combine that 1/4 and the 1/2. Because the original equation has a 1/2, so we're gonna keep that for comparison purposes. So pull that 1/4 to the front. Just like you did, that's a perfect strategy. Then 1/2. Yeah. Yep, and that's K1. And this is K0. Yeah, that's the strat for it. Yeah, that is exactly the way I show people because that works for any kind of problem like this. If you double the mass or half the mass, you can do the same. Pull all the numbers to the front, and you just want to preserve that original because ultimately I need to be able to. If you had pulled that 1/2 out, MV squared doesn't equal K original. 1/2 MV squared equals K. All right, 5 more seconds. 5, 4, 3, 2, 1. All right, so here's the strat, y'all. Here's how I do these problems, these ratio problems. I'm a big fan of them. So M1 equals M2. Their masses are the same. Actually, let's do this differently. M0 equals M1. And, do it this way. M1 equals M0. V1 equals 1/2 V0. All right, so this I write all my variables in terms of the other variables. So my masses are the same. My new velocity is 1/2 my original velocity. Why do I do this? So the original kinetic energy is that 1/2 mv squared, just with a bunch of zeros next to everything. My new kinetic energy is the same thing, but with a bunch of 1s next to it. Great. Now I just replace them. So I'm going to replace M1 with M0, and I'm going to replace V1 with 1/2 V0. And you got to be careful to square that. I think everyone kind of did this stuff, but this is just the methodical way of doing these problems. This is one way of doing it. So great. You get 1/2 M0 times 1/4 V0 squared. You pull that number to the front. You pull that 1/4 to the front. And ta-da, look. These two things are the same. This and this are the same thing. Now, it's very likely that you all did not need to do this for this problem. That you were kind of able to think through the logic here and solve this. And that works. And that's totally valid. I can make this problem more complicated by saying, if I want to make the kinetic energy 8 times as much and I half the mass, what do I need to do to the velocity? And trying to logic through that can be a little tricky, but if you set up this kind of system, if you solve for the things you want, I'm going to give you all more and more ratio problems like this. If this changes and this changes, how does this change? And this is the methodical way of solving it. Solve for the variable that you care about, the one that's changing. do all those substitutions, pull the number to the front. Works really well. Works really, really well. You can also make up numbers. Totally valid. All right. Great job, everyone. Woo. We did it. Okay. So you already derived this next slide, but so now it's in official words. Work equals a change in kinetic energy. It's great. Work equals a change in kinetic energy. This work can be done by all sorts of things. Gravity, friction, air resistance, someone pushing it. If something gets faster, energy is added to the system. If the system gets slower, energy is taken from the system. And this equation reflects that. Work equals 1/2 mv squared final minus 1/2 mv initial squared. And yeah, that's just kind of the rest of these slides. It's just doing this. So, work equals a change in kinetic energy. This is kind of the last thing I just had to cover that we didn't get to last class. It's what we'll be doing our lab on today. Our lab today, you'll be tossing a ball upwards, and you're going to calculate the average work done by air resistance and friction by looking at the final and the initial velocity. You won't need to know anything about air resistance, but you'll be able to calculate the average work done by it. It's a really, really handy tool. So, and we'll go through some problems today showing how this is so useful. There's a lot of problems in the problem set that show that this lets you find things that would otherwise be a pain in the butt to calculate. All right, so just a reminder to y'all. Scalars versus vectors. So when we worked with vectors, positives and negatives came from the picture. Remember you all drew arrows? And if an arrow was to the right, that's positive. If an arrow was to the left, it's negative. If an arrow was up, it's positive. If an arrow was down, it's negative. Scalars, the positive and negatives come from the math. When you're doing these problems, do not put positives and negatives in because energy is always a scalar. All this stuff, the only time, it just comes from the math. Even when you're doing work, I guess you get the angle from the picture, but then the math tells you whether it's positive or negative. Everything we're doing with energy, positives and negatives come from the math, not from the picture. Okay? So even when you all plug in gravity into these equations, do not plug in negative 9.8 when you're working with energy. It'll be positive 9.8 because we put everything kind of as positive, and the math tells us whether things are positive or negative. Vectors, we worked with positive and negative differently. So that's just a reminder. All right, and the reminder to you all, how do you find the sign of the work? If they're lined up, then the angle is 0. Cosine of 0 is positive 1. If they're anti-parallel, then they're opposite to each other. Cosine of 180 is negative 1. That's just a reminder. That's going to come into play when you all solve problems. Positive work, energy is added to the system. Negative work, energy is taken from the system. And that comes from the math. All right. So this problem is an example of how useful work and kinetic energy is. I've got a hill here that is not straight. It's bumpy. You cannot solve this problem in any analytical way with kinematics or forces. So this problem says I release 100 gram, that's not kilogram, so keep that in mind. And it slides down the path shown below, reaching the bottom with a speed of 4 meters per second. How much work does the force of friction do? And there's something subtle to this problem. This problem is a little unfortunate because it does kind of, we got to care about gravity a bit. So I want to point out something to you all here. Actually, you tell me when we use this equation, we're going to use this equation. I'm just going to tell you that now. Work equals the change in kinetic energy. I want you all to know this is net work. Net work. All the things doing work. And my question to you all, what is doing work on this block? Gravity and friction. So when you all get to step 3, I'm kind of giving you the equations. It's probably, literally the slide of this says work and kinetic energy, so that's probably fairly straightforward. You need to find the work of gravity plus the work of friction. Whenever that equation, work equals change in kinetic energy, it's net work. It's all the things doing work. You don't just put the work through the friction. That is the mistake that people make on this. So I'm just going to point it out now versus later. And we don't care about the path it takes in this equation, y'all. That's the cool thing with it. So anyway, write down your givens. Write down what you're solving for. I kind of jumped the gun and gave you all the equation. Make certain you understand where this equation comes from. Don't just say, yep, that's it. Use some brain cells. Make certain it makes sense where that came from, why we're using that, and then do it. Try it out. Oh, and I'll put the answer up there. I don't know what it is. What is it? 1 point. It's very low. But it is 100 grams. No, that's very look, Conan, I very much trust your work for sure. I was like, I'm going to double check it here though, just so that I'm not giving people the wrong answer and then end up with a bajillion questions. But if I was a betting man, I'd bet on you being right. Yep. Look at that. Oh. Yeah. Good thing we checked. Yeah. The math will tell you the sign of it. Yeah, that's a great problem. It uses all the things. You're going to have to find the work due to gravity, which means you're going to have to use a different equation I have written down here. Yeah, you don't have all the equations here. What you realize when you immediately start solving. Yeah, go through the steps. What's given? Oh, also on this test, please, on future tests, write your givens, y'all. A lot of people did not write their givens in a nice list, and so I couldn't really give points for that. Just make a list of like, M equals this, V initial equals this, V final equals this. You all have an insane amount of time on the test in this class. If you're not sure how to solve the problem, at least write that down. And then step 2, write down what you're solving for. Blank equals question mark. It may seem silly. 1, it's helpful to you. 2, it helps us give you all points. Like, otherwise I have to try to figure it out. And if it takes me more than a few moments to figure out what the heck you have written down, I don't spend a bunch of time on that. So, be organized in your stuff because it makes it more likely I'm going to give you partial credit for things. So this is going to equal work due to gravity. It's going to equal work due to gravity plus. It's going to equal the net of all works.
So, yeah, that's why
I was putting it in so this one you're just going to say plus WF. All the works together equal this change in kinetic energy. All the things adding and taking away energy from the system contribute to this. That's work. No, that's not work. This is net. F is units. That's units. Yeah, because that equals the work done or the work done. Yep. What are we doing in the morning?
Wait, is it the same?
And you even told me that.
So again, just getting good practice of this, y'all. Mass is 0.1 kilograms. V initial is 0. And if you all do these steps, you're also less likely to make mistakes. If it was a waste of time, I wouldn't do it. Ah, thank you. What do we want to call? Yeah, we're just gonna.
If you go back to that, the F.dr, the dr is down, the force is also down, so it causes.
Okay, so it's that equation, but it's just
Yeah, it's that, but we like proved it last time that no matter the path, or if you like, even if you throw it up that lands here from the starting to the final, you just take two. Because it's conservative.
So yeah, you all tell me, how do I get the work due to gravity? I didn't tell you how to do it. I mean, I have told you how to do it before, but not today. How do I get the work due to gravity? You know everything else. You know M, you know V final, you know V initial. We don't know work due to gravity. How do I find that? Yeah.
It's the force of gravity times the distance.
The work due to gravity. So remember, y'all, work equals the integral of F.dl, which looks gross. But remember, gravity is nice. Gravity is nice where we actually don't care about the path. The force of gravity is a constant. So we have Fg. You know, let's just do this times the path it takes times cosine of theta. Gravity is nice where the force of gravity is a constant. We don't actually care about the path of the angle. So it ends up being that it's the force of gravity, the magnitude of that, times how far it goes, times the cosine of the angle between them. Yeah, we could put, instead of d, we could put like y. F. Yeah, I got rid of the integral. Here it was an integral. Distance. Which way is my thing moving? Down. Which way is the, so what's my angle? Gravity is contributing. Gravity is adding energy to the system. Makes sense. It's making it go faster. So in this case, mathematically, we find that work due to gravity is a positive. There you go. So yeah, try that out. I'll give you all a few more moments on this. But this is like a classic work kinetic energy problem. And again, it lets us find something that you really couldn't find with kinematics or forces. The energy lost due to friction, good luck finding that with kinematics in this problem. It's disgusting. I didn't have to give you the coefficient of friction. I didn't have to give you, who cares what the path of that was? All I had to give you was initial velocity, final velocity, and how high up you are. That's it. That doesn't what? Sure. You know, but that'd be complicated. Getting that function would be tricky. You'd have to map that surface. Would be much harder. This is a simple. So that's technically what you're doing when you're doing the work due to gravity. That is the change potential. Yep. Yeah. And so this is kind of a foreshadowing that the work due to gravity is the negative change potential. Okay. They're the same thing. Yep. Everything gets derived from work.
But it is so it is final. But is zero.
I could easily change this problem and say it starts with initial velocity of 1 meter per second. Find the work done, and it would be a different problem. All of y'all are stumped.
Question. Is this for friction also?
What's cool is you don't need to. So we're not finding the force due to friction. We're just finding the work due to friction. Because if we look at this equation, so according to this equation, here, if I find the work due to gravity, and I know the mass, and I know the final velocity, and I know the initial velocity, if I plug that all in, I can find the work due to friction. So yes, there is another way of finding it, like doing, but that would be awful, doing the integral of f dot dl, because that would, the force would change the entire. It'd be impossible in this problem. So this is the benefit of the work connect energy here. You don't need to know the path. You don't need to know the coefficient of friction to find the energy loss. Oh, that's the That answer should be good up there, but let me get a good. There's some, your logic is all fairly good. There's some sign somewhere, and I just need a calculator to figure out where that is. I was like, it's something out there. So your logic was all good. That's how I knew it was good. There you go, great. You know what you're doing. Your process is good. We got 9 out of 10 points on the free response. Yeah. All right. So there you go, y'all. There's this problem. We'll do one more. If you show this work on the test, this is 8 out of 10 points. This is 8 out of the 10 points is doing all this and not plugging the single number in. Because if you show, this is the physics. Step 4 is just doing math. Step 4 is just the math part. That's the last 2 points. Did you make a math mistake somewhere, put the wrong number in the wrong spot? So the good news is, this is why I keep encouraging you all, write this stuff down. You will also find that if you're having challenges in this class, as you do this process more and more, it'll become more and more natural and problems will get easier for you.
I just thought about it, but will we be able to see like our work from the test and stuff?
If you all want to see your work on the test, yes, I have them all in my office. I will dig through the stack if you come by, and I will try to find your name. Yeah. I'll have to dig through it. If you want to see your free response work, probably shoot me an email in advance so that I can dig through the stack and pull yours out so that when you come by, I have it ready. Because it's a stack of 100. And I don't think they're organized alphabetically. So, I didn't organize mine alphabetically. All right. Okay. Forces to remember, because if you're calculating work, you may or may not do this, like we did it for gravity just now. Fg equals mg. The force of a spring equals kx. And the force of friction equals mu Fn. Fn often equals Fg, in which case that ends up being mu mg. The next problem is going to be with a spring. So that's why I'm reminding you all the spring force. You can find the energy, the work done by a spring, i.e. how much energy it adds or takes away from the system, depending on the frame of reference. So yeah, we'll kind of set up, I'll put this last problem up here. Y'all will kind of chug that out, try it out. And then we'll go into lab today where it's going to be a very basic lab, but you're going to use it to calculate the energy lost due to air resistance. Something that would be previously very challenging to calculate. Well, especially because I hadn't used the word energy before. But we'll calculate the average force due to air resistance as well. Something before that would be very difficult for y'all to calculate without energy. All right, boom. A 3 kilogram block is pushed up against a massless spring. Force constant 4.5 times 10 to the 3 newtons per meter. The spring is compressed 8 centimeters. When the block is released, it slides 2 meters from the point at which it is released across the horizontal surface before friction stops it. What is the coefficient of kinetic friction between the block and the surface? Draw a picture, y'all. Give y'all a few moments. Draw a picture of this. That's a lot of words. Make it look like a picture so that it's easier to understand what the heck is going on here. I'm going to use the wording it says and hope that this problem, well, the answer I'm going to get is going to be based on the wording it's using. Sometimes OpenStax, they neglect some things. Because technically the thing is moving both the distance that the spring is pushing it.
Oh, yeah.
Yeah. But I don't know if it matters. Yeah, it's good for them. It's like the real world. All right. So, draw a picture, y'all. We got a before and we got an after. So, let's just put a wall here and a floor. So we got a spring with a block that's compressed. The spring is compressed. So, I guess I'll draw 3 pictures. You got a spring, and then you got a spring that's compressed, meaning that the amount that it's kind of squished is 8 centimeters. Hopefully at this point, 8 centimeters is a trigger word for you. That shows that you don't like it and you convert it to meters. Anytime you all see centa, milli, grams, those should be like triggers in your mind that you got to convert it. The more you do this stuff, the more it will become that way, if it isn't already. All right, great. And then, at some later time, the spring goes there, and at some point the block's chilling over here. It has moved. What's cool about this problem is we don't care about the in-between. That's what's really cool about energy. We only care about the beginning and the end. We don't care about what happened in between the two. We don't need to draw a movie of this thing. Okay, step 1, write down all your all's givens. We're going to kind of go through this in stages. I mean, feel free to work ahead, but I'm going to work through this y'all in stages. Write down all your givens. Yeah, this is going to be a fun. We're going to have to put 2 kind of X's here. X compressed and how far it traveled. Yeah. So that's going to be a fun one. we have two kind of X's to consider here. So to that end, make sure you put little subscripts to distinguish which is which. As you're writing your givens, you'll see what I mean. That's fine. You can call two different things X as long as you put little subscripts that describe what they are. All right, so y'all tell me, what do we got? What's our givens? Mass. What else? And I'm only going to write down the givens you all tell me. If we need more, we'll figure it out later. Force? We have the coefficient. Yeah, we have the force constant. Does anyone know what letter that goes with? That's when you're writing down your givens, it is critical that you recognize what letter it goes with, because that's going to determine when you use your equations. What is the letter for force constant of a spring? K. Lowercase k. All right, what else? There is so many givens in this, y'all, and throw them out there. You lose, we need more than this, that's for sure. We know x equals 8, and which x is referring to? Is this how far the block slides, or is it how much it's getting compressed? All right, so I'm going to put x comp. You can write the whole word compressed if you want. 8e the minus 2 meters. Great, what else? Final position is, and if we have a final, what's my initial? Good. All right, any other givens? There's two more that will be beneficial to us, but we can discover them later if we're not sure what they are at this time. All right, let's discover them together. Let's discover what those... All right, step 2. What are we solving for? What does this problem want us to find? The coefficient of kinetic friction. What's the symbol for that? Mu. Mu k equals question mark. All right. Now we're going to choose the equation. I'm going to give you all some time. How the heck are we going to solve this? I'll give you all a hint. We're in a section called work and kinetic energy. We're probably going to use those things. On the test, you won't be as blessed with that, but the whole test is either momentum or energy, so it's going to be one of those two things.
One meter is 100 centimeters.
Work kinetic energy there? Sure. So let's think through that. Work net equals change in kinetic energy. Do we know? Can we find the change in kinetic energy with this problem? We figure it out. Yeah. What's my initial velocity? What's my final velocity?
Yes, that's 10.
Is the thing moving at the end?
Oh, because it stops it.
All right, so reminder to y'all, one of the hints here, the title, work and kinetic energy. So, we're probably going to use work and kinetic energy. So let's think through that. work net equals change in kinetic energy. So work, what forces in this problem are acting on it? What is doing work to this system? And the direction it's moving, or anti-parallel to it, what's affecting it? The spring is pushing it, so there's work done by the spring. What else is doing work to it? What else is speeding it up or slowing it down? Friction. Is there anything else? Is gravity doing work on this? No. Why? Why? Gravity is acting on this. Why isn't it doing work? Because of the direction of it, y'all. Yeah, which way is gravity? Down. Which way is my thing moving? What's the angle between those? 90. It does no work on it. Gravity is not speeding up or slowing down this object. That's what work does. Work causes things to speed up or slow down. So, and now we're going to start to see two variables that we didn't talk about, V final and V initial. What is my initial velocity in this problem? What's my final velocity in this problem? That's useful information. And what's cool, y'all, is you can always go back to step 1 and add this. You can always go back to step 1 and add it. If you think there's something that might be useful, think about the problem, and then you can always go back to step 1 and add that information to it. It's not like once you leave step 1, you can't go backwards. It's very, very common to realize, oh, I might need this. Is that the problem? Oh, look, it is. Okay, now there's one last thing I'll kind of leave you all with. So when we solve this, so if I take this, basically we find that the work due to the spring plus the work due to friction equals 0. Final velocity is 0, initial velocity is 0. So we find that the spring and the work due to the friction are opposite of each other. Spring speeds it up, friction slows it down. Makes sense. So the last thing I'm going to ask you all, and we'll kind of figure this out together. How do I find the work due to the spring? So work due to friction, we'll put that. Work due to friction is going to equal the integral F D, it's always the same thing, y'all. Integral FF DL cosine theta, which is, we're going to find the average force. So long story short, this one's just going to be FF times how far I move times, what's my angle between the direction it moves and the friction? Let's check. Which way does my thing move? Which way does friction act? So what's the angle between them? 180. Just makes it negative. Makes it negative. That's going to matter. Otherwise, they can't equal each other. You'll see that for yourself when you do the math. The work due to a spring. This is the one I'm going to work with you all. We'll get the equation, and then we'll kind of leave it here, and I'll leave the rest of the problem for you all. The work due to the spring. Work due to spring. I am not going to try to keep cramming this in this tiny space. That's just going to get really confusing for you all. All right. I'll set this up, and then we'll kind of enter a break time where you can either choose to keep working on this or whatever. And then we'll do the lab. So through the power of a green. All right. Work due to spring is the exact same logic, y'all. The integral of F due to a spring, dl cosine theta. What's the force due to a spring? What's the equation for that? Kx. So instead of dl, what are we going to put? What are we in x, y, z, r? dl is going to be x. And this cosine of theta, which way is the spring pushing the thing? To the right or to the left? To the right. Which way is it moving? To the right. So therefore, what's the angle? Great, so it keeps it as positive. Now, we do need to put some bounds to this integral. This thing is getting squished, and I don't want to end up with a net thing through which one doesn't give me a negative. Yeah, I think the negative's going to pop up. All right. How much is it traveling, y'all? So it starts at some location, 0. And then how much does the spring actually push it? Does it push it to 2 meters? The entire distance that thing is moving, is the spring pushing it? Or is it the 8e minus 2? This is where, and I'm going to highlight this, X compressed. The spring doesn't push it the entire 2 meters. That spring is not pushing this thing the entire 2. I mean, that'd be a spring that's this big. Like, that's not it. The spring is only pushing it however much it gets compressed. However much it gets compressed, that's how much it's going to push it. So, that's the key to this problem, y'all. If you all put that the X here is 2 meters, you are saying that the spring is pushing it over the 2 meters. It's not. It's only pushing it that little bit that it got squished. All right, so we'll leave it kind of here, y'all, and then you can kind of do the rest of it. Think through it. Reminder to you all, these problems, if you practice this on your own, they're best done from scratch. Because at this point, all the physics is actually done. And that's the part that I need you all to learn. Thinking through this is the hard part, getting to this place. So feel free to look this over. This is a reference, all those kind of things. But otherwise, when you solve this on your own, do not start here. Do not start at this slide. Because you're not learning anything. You're learning how to do math at that point. And I'm not testing you on math on the test. So anyway, all right, study strategies. So there you go. You got a few moments. I'm going to get the lab kind of all ready for y'all. It's not posted on web courses, so I'll quickly do that. And then, we'll do the lab for today. So y'all got a few minutes. Take a breather. We'll call it 9:27. Feel free to do this. Feel free to take a brain break, whatever is best for you. Oh, and Leo, Angelina, I don't know if you all knew that. This is something I learned recently. You ever have a Google Doc? See where it says up here to edit? If you delete that and you put the word copy, and you copy that, if you give that link to someone, whenever they click it, it'll ping them for if they want to make a copy of the document. Super, super handy. Yeah, I learned that with the whole COVID thing.
So you don't give them access to the actual.
No, you change the URL to the word copy, and so now when they click on it, it will say, "Hey, save this as a new copy."
So it'll become their own document.
Yes. Yeah. It defaults that to them. So, for example, if I now take this and I paste it here, I get pinged with this, and it automatically makes a copy for them in their own Google Drive. Super, super handy. If there's ever a document like this. Yeah, learned that in COVID. Because I had to make a bajillion for high school. Thanks. Yep. One of those things. Now you still do have to. I don't know why it defaults to this. I'm sure it did it. The restricted. No, good. It always defaults to the restricted access. Which why would? I've never wanted the restricted. Restricted access is always a pain. Angelina, are you good with me deleting The old groups.
Yeah, all
Okay.
the last ones.
Awesome. Yeah. Do the students have they been uploading it every single person, or is just one person? Okay. I guess that works fine. If we ever need to check it, we'll just ask them who uploaded it. Yeah. What's up?
So
Yeah. Good
Chris,
job.
right?
You derived the equation for the energy in a spring. We're gonna actually see that next week.
Okay. And then so once I need to find the coefficient of friction, but I'm not sure. Am I supposed to integrate this and then with respect to what?
No. Friction. Sure, you can integrate it. Does the coefficient of friction depend upon this?
The displacement.
Yeah.
Does it? No.
No, it's a constant. Does mass change based on this? Does gravity change?
So then
It's just distance.
Okay.
Yep. And that's the whole
So
idea
then-
of it. So it just becomes U mg times d.
Yeah. And then I'll just like work that out.
Yep. Yeah. Then you just solve for me. Yeah. You're there, man. Okay.
Yeah, you can't. Yeah.
Goodbye. Yeah. Lab group 45. Get out of here.
No, they're not open yet. Yeah, I do forget. I got lucky.
We have lost a single student in this class. I don't know that someone's always going to drop. Yeah. That's fine. Things happen in life. I never take any offense to any of that because it's, life happens. There's all sorts of reasons people might drop a class. They dropped it before the test, I think. That's the one test that we don't have because they dropped it. So that's good. That's one of the ways I check if I lost any papers. Is just how many students have a 0.
What was the answer?
It's a good question. It's in the problem set, and the answer is 0.25. Did you not get that? I got it.
It's just like harder. Right?
This might be negative.
Yeah, you're the first thing.
So remember, friction is also yeah, so this is perfect.
Yeah.
This will turn negative. So you subtracted this over that. This is also force of friction. Cosine of 1 becomes positive and it'll all like Yeah, I don't have the procedure written out here, but we can develop it together. That's what we'll sell this as. I'll make a nice new document. Yeah, what's up? Because the angle, which way is the so friction's this way, and which way is it moving? So what's the angle? Moving this way. So therefore, yeah, cosine of 180 is this. Yep, perfect. All right. So we're gonna go ahead and jump into the lab. One thing I want to point out that I forgot to mention. So I sent out that exam one survey and I put a link to it, and that link I failed both times. Yeah. It's right here, y'all. If you go to quizzes, it's there. It's just an assignment that exists. If you all go to the home page and you're like, man, I can't find it even in the quizzes tab. It should be somewhere. Look, there it is. If you all complete this, so I've actually already accounted for this. If you all complete this, you get an extra 2%. If you've already done it, I've already incorporated that 2% in your grade. Otherwise, once this is done, I'll go back and double check again. Really straightforward process for me, but it is due this Saturday. I've given you all an extension on when that's due. It's a very quick survey. Look, I'll just show you all the survey. Very, very quick. The benefit of this survey is it gives me feedback. So I ask if you've taken physics before. Why do I ask this question? It's because I want to distinguish between people that have seen physics before and people that have not seen physics before. It's very likely that the people who have seen physics before are going to answer that things were easier. So I want to make certain that the data I'm getting, it's one of those, is there a conflating variable? I am not the only thing that determines your knowledge of physics. Some of you have already had great physics professors before, teachers, whatever. And so that's why I'm asking this question. And so when I look at this later, I can determine if people found it easy who hadn't taken physics before. All right, great. And then, a bunch of questions. And at the end, there's an anonymous survey just to provide anonymous feedback that whatever you can put whatever. It's not linked to your email or name or anything. You could just put nothing if you want. It's up to you. All right. As always, you must assign yourself to a lab group now. I reset the groups every week because we tried that, not doing that one week, and that was a disaster. Find a group. One person's not a group. We will find you if you're in a group of one, and then we will find a group for you. Max 3, same old thing. Yeah, so don't use the link in the announcement. It's in the quizzes tab, or if you go to the home, it's an assignment. It's just a normal assignment. I try to make your life easier by putting the link, and the link I posted for reasons.
How'd you end up with the same link?
Well, so I right click the assignment, hit copy link address, and I post that, thinking that. And usually it hasn't passed me, so I don't know why it's not working. Yeah, I saw you post this. You sent me a thing with the URL stuff. I don't know why it's putting that. It's everything up to this point. I've adjusted all the quizzes. I've adjusted it. It's accurate with the caveat that currently the effort-based points are because the final is not part of the grade yet. So I told you I'll 50% is effort. Currently, because the final is not part of the grade yet. Yeah. So that's the one caveat to this, that this is pass mark theory. And that's what I told you I'll preview. Yeah. All the effort-based points are going to do this down pretty easily. Well, I need to look into that. It might get it posted weird. I can't look at it now, but I'm going to make a note to check that because that's not correct. All right. I apologize. There might be some errors with the free response grade that I need to check today because I've heard, I guess, the highest grade for the free response is a 60, which doesn't make sense because it's out of 40. So I'm gonna double check that. I'm not sure what happened there. Yeah, I'm gonna check that. Something's wrong there. So anywho, things might shift. I'll update you all. I'll get that done today after this class. My apologies. I generally try to I did double check it, but I clearly didn't double check it well. Very odd. I'll look into it. All right, y'all. Find some groups. 34 of y'all still ain't in a group. Sure. Who's got a group of 3, 2? All right, so they're in that group. Are you all a group of 2? Yeah. There you are. They're solid. They'll treat you well. Thanks. Yeah. All right, 33 of y'all. I'm going to give you all like 2 more minutes. You can go ahead and jump to the lab. If you want to open it, feel free. You can start perusing it, and I'll start talking through it in just a second. Oh, we're getting there. All right. Well, if you're still joining, you're still joining. Okay. So, work in kinetic energy lab. Going to be a very straightforward lab. You'll be using equipment that you all have used in the past. So you're going to use a ball. You're going to use a smartphone. You're going to use some meter stick. Do we actually need a mass scale? I think we do. So we are going to actually, I think, have to take the mass of things. I think we are. So you are going to have the pleasure of using some really, well, they're like the old school mass scales where you have to slide things and find things. I don't know. I don't know if they're better or worse, but they're what we have. So they're the best currently. All right. Look, a bunch of words about things I taught you, courtesy of ChatGPT. Yeah, I'm going to warn you all. This is the first lab that I have made from scratch. I have exhausted the labs that I have, almost exhausted the labs that I pulled from previous instructors. It does not mean this is a bad lab. It just might mean, this is my pilot test. So we'll see. The other labs have been tested. So you all are my beta group. It's going to be fine. Beta testers. All right, to that end. First thing is I want you all, this is going to be a norm moving forward, try to come up with a procedure for how you can measure the average force due to air resistance for an object tossed straight upwards using the following objects. An object with a known mass, a phone, and a meter stick. How, using the principles we have learned in the last 2 weeks, work, energy, work, kinetic energy theorem, what experiment could you do to determine the force, average force, very important that the word average is there, average force due to air resistance? Deliberate. We'll come up with a procedure together, y'all. The reason we're going to do both is so we're going to tell some which way is the force to the air resistance and which way is gravity. So they're the same direction. Whereas on the way down, which way is it? Gravity is. Once you get some asymmetry, which is hopefully going to be cool. We'll see. My hope is you can see that in the graphs. We'll see if you can see that in the graphs. I don't know. Yeah, so at one point they're both pulling it down, at one point gravity's moving it up. Yeah, you gotta make sure. All right, give y'all a couple more minutes. Pro tip, we're going to be using Tracker soon. So the force to air is so it changes based on velocity. So as your ball is moving, its velocity changes. It depends upon the shape of your object. Yeah. And the shape of your object.
Can I ask you a quick question? Huh? Okay, I know you just showed me this, but I just want to make sure I see that right.
So you have to know the density of you find the cross-section area. You have to look up this constant basic shape of the sphere, and then you would have to have velocity like it's all good. You don't need to do that. Basically, we have to use Maybe. I asked him. I haven't taken him potentially, but you'll probably spend a lot of time. All right. So, what are we ultimately? What logic are we going to use to determine this? Like, it's the bread and butter we've been doing. What equations are we going to kind of use to determine this? Because you can't get this value just from Tracker Pro. You're going to have to do some calculations. How can we do this, y'all? What equations relate things to things? Things we can measure to things we want. Change in kinetic energy equals the work done. Change in kinetic energy equals the work done. So, let's make a nice little document for this. Fantastic. Thank you, Tabs. Don't know what that means. All right. So work, let's make this. Work net equals change delta. All right. What is doing work on my ball? What two things? Gravity and work. Yep, so we got the work due to grav plus the work due to air resistance equals delta kinetic energy. Now, I want to point out something to you all here, and it's going to come up in the lab. On the way up, let's draw a picture of this somewhere. I don't know if I can do it on. I'm going to have to do it on the PowerPoint slide. This is very, very important because, well, you'll see why. On the way up, we toss the ball upwards. It's moving upwards. Great. So our displacement is upwards. Which way is gravity? Down. Which way is air resistance? We'll call it friction. Air resistance is just another form of friction. Great. They're lined up the same way. So when you all calculate work, will those both be positive or negative? The work due to friction, will it be positive or negative if they're opposite directions? What's the angle between these, y'all? Are they lined up with each other or are they opposite? What's the angle if they're opposite? 180. Work due to gravity. Positive or negative? Are they lined up or are they opposite? Opposite. When the ball is falling, which way is air resistance? Up. When the ball is falling, the air resistance is going to be up. Which way is gravity going to be? So in this system, work due to friction, positive or negative? Are they lined up or are they anti-parallel? Negative. What about the work due to gravity? When you all are working on this problem, you actually have to split it up into two problems. You have to split this problem into two problems, on the way up and on the way down. Because in one part, friction and gravity are slowing it down. And in another part, gravity is speeding it up and friction is slowing it down. So anyway, I mentioned that. Real quick, going back to our lab before I kind of cut you all loose to continue doing this thing. So great, we're going to use this theorem. We're going to do the things. What do you all need to measure? What do you all actually need to measure to make these calculations then? You need to measure height. You need to know how far it goes. What else do you all need to measure?
Initial velocity.
Initial velocity and final velocity. I'm going to let you all kind of determine how to do that. There's many options. I mean, there's not that many options. There's a few options. But to that end, you are going to measure how high the ball goes. You are going to measure the initial velocity. And actually, you all know, what's the final velocity when it's at the highest point? 0. So actually, that one's kind of straightforward. So measure the initial velocity and the velocity when it comes back to your hand. And in all bold, all caps, split the problem into two parts. The part going up and the part going down. And based on what I have written in the lab manual, calculate what you need to calculate. Do not do the entire, if you do the entire path, you're going to, split it in half. Either look at the way up or look at the way down when you're calculating that average force. Okay? All right, have fun. Use Tracker Pro.
When you're being asked to measure the mass, we got 3 scales in here, we got 1 up here. If you guys both have the same mass at like a table, you can just share it.
If it's we're going to assume these tennis balls are roughly equivalent to each other.
Yeah.
But I don't know the mass of the tennis ball. Find it.
But you don't really have to rush to do it just before you submit it.
Yeah, you all can do the mass of it at any point. You know, like someone take the video, start going through it. Just at some point you will need it to calculate the work due to gravity.
As long as you have a meter stick.
So that feels about like 1 to go ahead and measure it. We all did measure it. Yeah, we definitely measured it. Otherwise,
Just get it after someone else uses it there.
Your software will your meter stick is only used to calibrate the video. You're not actually using the meter stick to figure out how high it went. Tracker Pro will do all the things for you if you calibrate your video appropriately. Hopefully you learned at this point what happens when you don't calibrate your video and your thing goes bajillions of meters per second. Yeah, I have no idea if these are more accurate than digital ones. I'd almost bet digital ones are more accurate.
Yeah. Because, like, this, it's like it's
No,
your
it is.
bias is involved in, like,
Yeah,
when you
a
think
little
it's
bit.
balanced.
Yeah.
6.
It all depends on how dinged up this thing is too.
That.
I think there's a. I think this is used for calibrating it. We would have to have a known mass to calibrate it against. Ooh, yours is different than his. Not all tennis balls are created equal, it seems.
On Google, I give you
Ooh.
59 points.
Yeah.
I don't think this this does anything. Yeah, I don't know if this one does anything.
That's
50 and 60. That's
so odd.
yeah.
Wait. Wait, how stiff is this thing?
I don't know. It's
This thing's just very
pretty
stiff.
Yeah.
Oh, that's so frictiony. Oh no.
Can I just tell them to use like 58 grams?
Something like that. You know, you'll end up with some error of 1 to 2%. You're gonna get bigger error. This thing's just sticky. Like if it's there, it stays there. If it's there, it stays there. Oh no.
If you guys feel like you can't get a good mass for a tennis ball, you can just use like 58 grams.
1 to 2% error.
Also, I made a awesome how to use spreadsheets sheet, and it's under lab 4. So if you need a refresher on how to plot your graphs and make sure things
Should be here.
I guess we're not plotting graphs.
I think it's here as well.
Oh, it's here.
Yeah, I copy and pasted the assignment. Yep. That's the beauty of
Initial velocity would be 0. The final velocity, your initial velocity is what, how fast you go.
I don't know.
The final velocity is how big it's going There seems to be a few groups over here that are down to the meter 6.
Oh.
If your video is sideways, remember you can change your coordinate. You can rotate your coordinate system. I've shown some of you all that before. If you're not trying to do it, ask me. Do not forget to calibrate your video to 1 meter. If you forget to do that, your data's gonna be crap, like real bad.
The force of gravity is down. Friction down.
Calibrate it.
So they're opposite to where it's going. So you gotta go back.
It's so weird.
It's literally the W that you put down.
So sorry, I didn't know it's misplaced.
I can see what it has in the beginning.
Yesterday, I took 1 hour to do one problem. Because I didn't know how to use it. Everything that we're doing now is required textbooks. And I don't know how to do
You don't need the ball anymore, right?
Alright, boys.
had a table
I appreciate someone doing that. All right, don't forget to scan the blinky blinky. Attendance is up. Attendance is up. Don't forget to scan attendance. This is kind of our backup way of making certain that at some point I will check this where I will compare the lab grades to the attendance. And they're discrepant. We got some sus people. And I will have to navigate that. So this is my backup way. We have to assign to groups, but this is my backup way of making certain I don't have anyone outside the class that just assigned themselves to a group and is getting credit for something they didn't do. It will get referenced at some point.
Sorry.
Yeah, no, of course. Go to. So you're going to click
Where?
to the right of that one. Yep. And then you can do that little. So currently it's saying this is up and this is down. Other way. Because you want up to be this way.
No, no, the big up.
Yeah. You just redefine which way is up. Yep. You know, up is all relative.
and then we calibrate it.
And then you just calibrate it like normal. Calibrate it like normal. You're gonna want to do your course. So this thing is where origin is defined. So you can combine 0, 0, that's 2. But in your case, currently it's saying this is one positive one. So you put this thing over here, you rotate it for the system. So now it's saying that's positive, that's up, and that's down. Yep, and you can do that anytime moving forward. You know, up is all relative. You turn your head, up looks different. You can do the entire thing. It's a great question. As you all are tracking your data, I recommend tracking the entire path of the thing. And then when you generate your plots, you can just highlight the data for the way up, and you can just highlight the data for the way down. It's up to you. You can either do 2 different tracking, or do the entire tracking, and in Excel, just select the parts you care about. It'll be really obvious what part you care about, because it's when the velocity turns to 0. That's the turning point. Last chance for attendance.